Okay, so as we said, as part of our development towards the analogies, we want to develop our heat transfer, and towards that, let's first look at our mass transfer framework. And let's do that with a little particle first. So if we consider the case where we have a particle in our space, so this is, in a sense, a real particle. And then we are looking at some distance away from the particle. So if we define some radial position, and just to emphasize, this is an imaginary position, then we can define all the transfer rates and the diffusivities and so on through that space. Okay, and so we can define for ourselves some radial position, and we are now looking at the radial position R, and we want to know something about the flux there. So that's radial position R. And we are interested in number one, the flux. So we know the flux in terms of the diffusion flux around the particle, that's one. But we also acknowledge that the fluid might be in flow. So that's something that we dealt with in flow in pipelines and so on. So if the fluid is in flow around this particle, then we will have a certain geometry to contend with, which relates to the position of the fluid and so on. So for now, if we assume that the velocity is approximately zero there, then we can develop the balance in the standard way. So we can say that the molar flux in at this point minus the molar flux out at that point, that can be related to the number of moles in the space. So the standard balance applies, and I'm just going to skip a couple of steps because this is something quite familiar to you by now. So the concentration at the radial position R times the volume of the space between R and R plus delta R. So let's create the other side of this. So we are diffusing between R and R plus delta R. So that's the other position. And you always start these problems with this kind of sketch, right? So you always want to illustrate your problem. And I'm just going to call it a DR over there. So if you write the balance on this, we can say the approximate number of moles in there is going to be the concentration multiplied by the volume. And so the volume of the space between the two blue lines, we can approximate as the surface area 4 pi R squared times the thickness delta R. And of course, we could talk about a more precise calculation of that volume. We could take the volume 4/3 pi R cubed at R equals R plus delta R minus 4/3 pi R cubed at R. And so that is precisely the volume. But we don't do it that way. We settle for this approximation because, number one, we know as delta R goes to 0, this becomes a better approximation. So this does converge to the real volume difference there. And also choosing it in this form helps us to cancel things out. So it's convenient for mathematical reasons. So that's the rate of change of moles in the space. And then the arrival by diffusion, so the diffusion flux into that space is dA, and we'll just call it effective diffusivity. And then the gradient there is dCA, just put a dot in here, dCA dr. So that's the gradient, and this is evaluated at the R position. And of course, this is only the flux. It's not the molar rate of change. So we need to multiply by the area at that point, which is 4 pi R squared. So that's the area normal to the flux. And then that's what's arriving into the space. So that's what's arriving into this, this control volume between the two blue spheres. And so leaving that space is minus, and then the flux there is again minus. And then we have here a dCA, dR, dAe. So that's the actual flux. And this is at the position R plus delta R. And then in this case, the area is going to be evaluated at R plus delta R. So that's our complete balance. And of course, then we can rewrite this in the form dc dt of Ca equals, and this is going to be a plus, and we're going to get here an R squared 1 over R squared. Okay. And then a d2 Ca dr squared, or rather a ddr, let's rather do it this way, ddr of R squared dCA dr. Right, so we've done this before. So if you go back and look at the spherical geometry, this was what we derived for the sphere. So this, of course, covers, or this fully describes all changes in the fluid at any position R away from the sphere. Now, as we start looking around the sphere, we realize that, yes, you can write such an equation, but if you actually go and plot the changes of concentration away from the sphere, it might be the case that the concentration changes only happen up to a certain point, say around there. And after that, it becomes fairly steady. So let's just draw that a bit better. So your concentration changes all happen within a certain region. And then beyond that region, it stays pretty uniform. So in film theory, we recognize that instead of trying to estimate the concentration change over any distance, and maybe this is a long column or something like that. So instead of trying to run our model all the way over tens of meters, we can recognize that, well, most of the action is only happening in a very short space here. It's only happening perhaps over 5 millimeters near this surface. So we can say that we anticipate that all the changes that matter to us probably only happen in a very short space near the surface of our particle. And if that's the case, then we might as well define a region here, a film, in which we will recognize all the concentration changes. So in which we will calculate all the concentration changes and then use that towards our overall estimate of the rate of mass transfer in the reactor. So maybe to take a step back and talk about that, by the end of the day, we have some chemical engineering unit, or rather some unit in a chemical process. And there are many, many such particles in this reactor. So we might have tens of thousands of particles in this reactor. And so rather than trying to estimate the concentration gradient as it moves away from every single particle here, we want to develop a nice estimate for all the action happening near each of those particles. Or a better way to look at it is, that we want to estimate all the changes that are near a representative particle. So if we can represent a group of particles, so maybe 50 particles can be represented with a certain diameter, maybe 1 centimeter, then there's another 20% with a slightly different radius and so on. So we can think of classes of particles, and so we can add up the fractional contributions from all these particles. So that's, if you like, a kind of justification for film theory. So to calculate the associated constant, right, there's a Kc that we define. And so we say that, yes, we are aware that we have a dA, that the most rigorous way to do our calculations is in terms of a DAB, or an effective diffusivity, DAE, right? So we are saying that we acknowledge that this is the right thing to do. So we can say here, the actual molar flux, the most rigorously defined molar flux, or diffusion flux, is this. But we as engineers are saying there's a certain approximation that could be applied, which is to define a Kc. Well, it's not approximate yet, so let's just say equals. So we can say there exists some constant Kc, and what really matters is that the concentration difference that matters is all concentrated in a very small space. So it's between this point and this point. And we can go ahead and define the concentrations at these 2 points. So we will define this concentration as CAS, and we can define out here a bulk concentration, CAB, for bulk. So if we think about in our real reactor, if you look at all the space between the particles here, right, these particles are sitting in some fluid, whether it's gas or if it's fluidized, if it's fluidized, then it's a gas, or they could be suspended in some liquid. So there's some continuous fluid here, right, a gas or a liquid, and the particles are suspended there. And so in that fluid, we can define for ourselves a certain bulk concentration. So we can define a CAB for the bulk concentration. And so near our particle, we can say, yes, we know on the surface of the particle, there's a different concentration, CAS. But as we start to move away from that particle, the concentration changes. And then eventually we see the bulk of the fluid. So the bulk of the fluid in the rest of the reactor, that's where we observe the concentration CAB. And so the film then can be defined as this difference. Right? So if we take, let's draw a line like this. And then I'm just going to break this line. Yeah, the breaking is going to also overwrite my, unless I do it like this. Okay, let's try and overwrite some of this here. So I'm just breaking this line here. And so there's some line we can identify here, or some distance. So we are going to call this the film thickness. So the thickness here, we will call it a delta. I don't think I can make the right symbol here, but so I'll just write it delta. Okay, is there a question or comment?
Sorry, sir, just really quickly, what is that orange line again? What does that represent?
So I'm just pointing at the thickness of the film. So we have defined that near this point, right, at this radial position, we are close to the bulk value, right? And so if we are saying that all the concentration changes happen between the surface and where we get close to the bulk concentration, then this orange line represents the thickness of the film. And that wasn't originally what we meant by it. Originally, we had just chosen some arbitrary position R plus delta R. But now if we are drawing this green line to say we are getting close to the bulk concentration near this point, near where we did draw that blue line, then this line here, delta, that is the thickness of the film. Does that cover it?
Yes, sir, it does. Thank you.
Okay. So there's this concept delta now. And so we are proposing that there is a certain film thickness, and it hasn't appeared in our equation as yet, but let's finish what we are writing here. So on the surface, we've defined CAS, and at this position, we are at CAB. So we can say this is CAS minus CAB. Okay, so we want a form like this, right? So we are saying this is complicated to us. This diffusivity gives rise to gradients like this and derivatives, whereas we would like a nice engineering type of equation where we just take some constant and multiply it by the concentration difference that matters. So to our mass transfer here, the concentration difference that matters is the surface concentration and the bulk concentration. So those are two real, the bulk concentration we can measure. We anticipate that in this bulk fluid, we could take a sample of the fluid and run it through a gas chromatograph or something like that, and we can estimate a concentration in that bulk fluid. On the surface, it's harder. It's not clear to us how to take a sample from the surface, but maybe this is just a construction variable. So we'll at least define a CAS for now. And then we'll say, then that's a simplified version of this. So film theory is nothing but an attempt to simplify our function here. And then the other approximation in film theory is that, well, if we are just looking at it as a simple difference between two concentrations, then we are also going to just say there exists some average gradient across those 2 points. So the average gradient there is something that we can write as, so we can rewrite the average gradient. If we were to rewrite this, we can say that over the range R to R plus delta R, there exists an average gradient, and that average gradient will look something like this. So it's going to be minus DAE, and that average gradient will be obtained by taking CAS minus CAB and dividing that by the difference in radial positions. Now we have already defined the, we've defined R and R plus delta R, but you can define this radial position in terms of the film thickness. We can define this to be, this is going to be delta. So the thickness here is delta, and then we have to add the radius of the particle. So this is delta plus R. And then over here, we have the radial position R. So capital R is the radius of the particle itself, right? So this is the position R. Then we said delta was this film thickness. So this is the position delta plus R. So if we take that, at CAS, the position is R, and then at CAB, the position is R plus delta. So delta, it's the lowercase delta, right? So that's an estimate of the gradient. And so if we look at what's down here, this is nothing but a delta. Well, it's nothing but delta, right? So we can rewrite this as dAe divided by delta times CAS minus CAB, right? So if you look at this expression, R minus R, that vanishes, leaving us with a minus delta. And so minus dAe over that minus delta, we can rewrite like this. And then the numerator, we just retain it over there. And then if you look at what we proposed up here, we said that that molar flux equals this. So that equals that. And so looking at this equation, we can just get rid of the driving force. So we've got the same driving force term on both sides. And that gives us the relationship between diffusivity and your mass transfer coefficient. Okay, so that's the approximation that we come up with. We know that if we were to integrate, we would get this green curved line here. This is the rigorously correct thing that happens in nature. But once we do that, we are then committed to estimating the profile over the whole distance. Instead, we are saying that all the changes are concentrated in a very small space. And so we will acknowledge that there exists some average gradient across this space. So that average gradient can be defined if we define a thickness of the space. So we say there is a position where we are approximately close enough to the bulk value. And then if we just define the end concentration, CAS and CAB, then that gives us the driving force. And then if we define the distance of that space to be lowercase delta, then that defines the delta R that we need as well. So all of that gives us this definition of the mass transfer coefficient. So now we have a nice mass transfer coefficient. We don't have to contend with gradients anymore, and that gives us a very quick way to estimate the molar flux. Okay, there is one, let's see, I think there was one thing. Oh yes, one thing I forgot to mention there was, of course, this green line is never actually identically equal to CAB. So as you get closer to the bulk value, then the driving force, right? So as your concentration minus the bulk value, as that gets closer to zero, then that drops the mass transfer flux. And so you never quite get to the bulk value. So this green line never gets to CAB identically. So we have to define some criterion for where this delta occurs. And the way we can say that is that we want to know the radial position where the concentration, let's see, yeah, let's do it this way. So we want the radial position where the concentration CA, equals, and we never get to the bulk value, right? So CAB, as we just said, we never get to the bulk value, but instead we define a kind of, again, an engineering approximation. We say there does exist some point where it gets to 99% of that bulk value. So the radial position where we have the concentration being 99% of the bulk value, that is where we define the film to end. So that's a radial position. So we can say delta, the film thickness delta is equal to that position minus the radius of the particle. So that's how we can rigorously define delta. It's where the radial position is 99% of the bulk value. And so that radial position minus, or rather that radius minus the particle's radius, That's the film thickness. Okay, does that cover the film theory? Is that enough revision on that?
Yes, thank you.
Thanks. Okay, and as I said, let's also take this opportunity to think about what this would mean in terms of the heat transfer as well. So imagine the situation where you are suspended in some fluid. So let's say it's a liquid. And in this liquid, we can define for ourselves a bulk temperature as well. So in this liquid, right, in the space surrounding this particle, obviously there exists a fluid, and in that fluid, the temperature is, well, we define it to be TB, the bulk temperature. And then let's imagine that we have an exothermic reaction happening on this particle surface. Then we can easily imagine that the surface temperature here is going to be higher than the bulk temperature. So on the surface of this particle, there applies a different temperature, Ts. And again, we anticipate that there is going to be some change in the temperature across this particle. And we could sketch out how such a change happens. So there's some gradient in the temperature. And then all that variation is concentrated in a relatively short space. And then we achieve the bulk temperature. So the same concept applies in the case of the thermal energy balance, right? You have a bulk temperature and you have a surface temperature, and the surface temperature may be different from the bulk because of whatever that particle is there doing. So if that particle is there to catalyze a reaction, for example, then the heat evolved during the reaction. If it's an exothermic reaction, will cause the temperature there to be locally different. And then if it's an endothermic reaction, then the temperature there may actually be lower than the bulk value. So the point is there's some difference in the temperature. And then again, we can imagine that in the same way that we have diffusion, we have also conduction. So across our particle, we have a certain rate at which energy is conducting away from that particle. So there's some conduction through the liquid. And so we can write a similar balance on the space. So we will define for ourselves, we need a couple of quantities to define all this for us. And so we need a way to count up energy. And I assume, I assume you've covered this in the thermodynamics course, right? The definitions of enthalpy and heat capacity and all of that. But let's assume not, right? So I'm not assuming that you know about enthalpy or heat capacity. We are just going to do all that from scratch here. So let's define enthalpy. So HI is, so let's say define HI such that HI times the, let's say this is the mass, right? So such that HI times MI is the energy in a fluid of mass MI, or we should say in a fluid containing component I at mass MI. So enthalpy is then the mass analog of energy. So enthalpy has units, so HI will have units of, and it's going to be joules per kilogram. And if we think about what type of enthalpy that is, and sometimes it's easier to think of it in terms of a temperature change. So you've got some fluid at a certain temperature. So let's say we have a 1 kilogram basis of fluid. And this is at some temperature T1. So this is sitting at an enthalpy H1. Now, if we go and apply energy to this, so let's say we stick a little heating coil into this fluid and we heat it up, and we now reach temperature T2. So after heating, we've reached temperature T2. Then, of course, that fluid has absorbed a certain amount of energy, and it now has an energy content of H2. So we are thinking of an enthalpy change in terms of a temperature change here, and that temperature change has been achieved by adding energy to this system, to this 1 kilogram mass here. So we can say that there has been some energy, there's some quantum of energy that has been added, and the amount that's been added is equal to the mass in there times the enthalpy, and this, let's say that's enthalpy 2 minus the mass there at enthalpy 1. And with respect to this fluid, we are simply counting up this enthalpy as the energy, right? Or rather, the way to say it is, we can't observe energy directly. The only way that when we look at this fluid, the only way that we can comment that the energy has changed is due to the temperature change. So temperature changes are what's observable to us, right? Nature is not going to define for us a certain quantum of energy. Nature is not going to say, oh, you had 50 joules in that box. So all that we can observe when we measure this fluid is a temperature change here, T1 and T2. So we have measured a certain temperature, and associated with that temperature, we assume there's a certain different enthalpy in that space. And so we can say then, well, number one, let's just divide by this MI. And so we would like a way to estimate energy changes due to temperature changes. And the way that we've done this, and you may have seen some of this in the prac, right? How many have done the practical where you change the temperature? Has anyone done that practical? Maybe thumbs up. Have you done a practical where you applied heating to some object and then you measure the temperature change?
No, sir.
Okay, so let's imagine an experiment like this, right? Exactly the same experiment. Let's just zoom in here. But exactly the same situation where, yes.
So just real quickly, what is that red line that you drew? It's like a sort of like a curve. It looks exactly like that green line, which shows like a change in concentration. What does that red line represent?
This line here, like an arrowhead, with the arrowhead at the end.
No, it's on the circle.
On the circle.
Yes, sir. It's this red line. It's just above
the
that
curved line. That's the temperature profile. So I'm saying near the particle surface, yeah, there's a surface temperature, and then there's a bulk temperature. So there's a different temperature in there. And then there's a continuous change in temperature. So that red line is just showing the temperature. So if we were plotting the temperature as a function of radial position, then that red line is that temperature.
Okay, thank you.
Okay. So we are now looking here. And what we do is we take an actual heating coil, and on that heating coil, we also have, we can measure the power. So the power rating on that. So we know how much energy we put in here. And we've got our liquid in here. We measure the starting temperature. We apply a certain amount of power. So we apply heating over a certain time period, and we know the wattage, so we can work out the total amount of energy we put into the space. And then we measure the temperature at the end of that. And so, for example, we can plot this as a function of time. So we measure the temperature, we are applying heating. So initially there was nothing, then we switched on heating, then the temperature rose, and then we stopped heating. So we've got a certain temperature change here. And so that's associated with a certain amount of heat that we've added. So the energy that we put in, the Q, that has caused this temperature change in this fluid. So if we know the amount of energy that was put in, and we know the temperature change, then we can say that we can estimate a gradient here. So we can say Q divided by delta T is equal to, and then there's a certain mass that we used in that experiment. So the liquid has a certain mass there. And then we say we would like to measure the heat capacity. So we define for ourselves a heat capacity. So we need some constant to relate the mass, right? So without this constant here, we can just say that there's a certain amount of mass that's absorbing a certain amount of energy, and we are observing a certain temperature change there. So to relate all these quantities, we need some kind of factor here that relates all of that. So that's what we can measure. We apply a certain amount of energy to a certain mass, and then we measure a certain temperature change. So the other way to view this is that there's a certain amount of energy we've applied, and we've observed a certain temperature change. So Q equals mCp delta T, right? So that's the energy needed to raise the temperature by delta T for a given mass of component I. And the way we can work it out from the perspective of the fluid is if we have the heat capacity. So if we just look at the fluid and we just measure the temperature change, then we can estimate the heat capacity, the energy that was applied if we have the heat capacity. So the heat capacity helps us relate the energy applied to the temperature change observed. Okay, so that's one, that's the heat capacity. And now we have introduced the notion of enthalpy, and that is also the energy content of our fluid. So our enthalpy, let's save this.
When I asked him yesterday.
Sorry, what's that? So now we've got this concept of enthalpy, and it's telling us how the energy changes as the temperature changes. Right, so we can plot enthalpy here, and let's just label enthalpy H, and we are considering different temperatures here. So we start at some initial temperature, And then as the temperature rises, our enthalpy rises. So the energy, as we apply more energy to the system, then the enthalpy is increasing by that amount of energy, and that's causing our fluid to heat up. Now, there comes a point where there's possibly a phase change. So let's say we were applying this heating to a block of ice. So let's say we started out as ice and we were applying heating. So you could say that we had subcooled this ice to begin with. So let's say the ice was initially at minus 200 Celsius. Then we were applying heating. So the whole block of ice, the temperature was rising. In fact, forget about the coil here. Let's say the whole environment was increasing in temperature. And so the ice temperature was rising. And then, of course, we get to a temperature of 0 degrees Celsius, 0 C. And at this point, the ice starts to melt, right? And at 0 C, the ice is going to melt. So the phase is changing. And so the energy that goes into melting the ice is going to, there's going to be an energy loss to melt that ice. And so instead of the temperature changing, you will lose energy at the same temperature. So during melting, just to convert the solid to the liquid, to break the bonds that make it a solid and to form the liquid, we will be requiring energy. So the energy requirement is increasing, even though the temperature hasn't changed. So the liquid is still at 0 degrees C, but we are losing the solid. Okay, and then at some stage after we've added enough energy to that 1 kilogram, then we have a pure liquid. And so everything is in the liquid form now. And so beyond 0 C, we are heating up a liquid. So if we add more energy to this, we are now heating up a liquid. And so this liquid temperature, the temperature will rise as we add more energy beyond the point of melting. Then we reach another temperature, which is the temperature at which we form steam. So we reach a point, right, 100 degrees, and we now start vaporizing our liquid. So our liquid starts boiling at 100 C. 100, and I'm just going to say 100 C like that. So at this point, we haven't boiled all the liquid hasn't converted to gas yet. So we need a certain amount of energy to convert all that liquid to gas, right, to steam. So there's a certain amount of energy needed for that. And then once we've applied enough energy there, then we are all in the gas phase, and beyond 100 C, we are then adding heat to the gas, and the gas is just getting hotter and hotter. So that's the enthalpy temperature profile that we have. And so we've been talking about this as if we are adding heat. So if you look at it from another perspective, you could say, well, if my fluid is at this temperature, let's say it's 120 degrees, then my enthalpy, then at some stage we must have added this amount of energy to the fluid. You can define a reference state. You can say at 0 Kelvin, nothing is moving, right? Remember the Kelvin definition that's related to the vibrational energy. So at 0 Kelvin, that's a kind of ground zero state for energy. So that would be a nice reference state. Of course, in engineering, the reference states are actually at some arbitrary temperature, depends where someone started measuring, and so you define different reference states. But so you define some reference temperature, and you say, with respect to that reference temperature, I must have added this amount of energy. So if we look between this current temperature and some other temperature, you can say this is the amount of energy that must have been added for me to be now sitting at this temperature at this temperature at this mass. So that's the enthalpy then at a certain point. And then we can also identify these slopes here. So we've got a slope, we've got a slope here in the gas. And this slope, of course, is our heat capacity. So remember, you could also think of this as, remember, this is really the amount of heat added. So we can think of this as a delta. So that's the amount of heat added to our fluid. And so we could say dq dt equals mCp. And then if you are doing this on a 1 kilogram basis, right, then you could say this is dH dt. So dH dt, and this is 1 kilogram. So our heat capacity is the gradient of enthalpy with respect to temperature. And I've deliberately drawn these slopes to be different because generally speaking, the rate at which we accumulate energy for every 10 degree, for every 1 degree rise is different in each phase. So as a solid, we absorb heat at a different rate compared with as a liquid, and so on. So we can say here, there exists a certain heat capacity here. So there's CP as a solid, and this is CP as a liquid, CP as a liquid, and this is CP as a gas. And so we have to use the right heat capacity. Furthermore, these lines are not nice and constant. It would be really a nice simplifying thing if heat capacity was independent of temperature for each, and by CP we meant the gradients here, right? So heat capacity, if you have a straight line here, that means CP is constant in that range. So remember, CP is the gradient dH dt. So that's heat capacity. The way I've drawn it, heat capacity would be constant in this range and constant in this range and so on. But generally speaking, it's not constant like that. Generally speaking, there's some kind of curve that applies, and it might not be a really regular curve either. But all that's tabulated. For many, many substances, we have the heat capacity as a function of temperature tabulated in our handbooks and so on. So you can get to that value. But for now, we'll just treat heat capacity as constant in each of the phases. So that's the concept of heat capacity. So all that is introduced because what we need to do is estimate, if we come back to our original problem. Let's find it. So looking back at our original problem, we've got that we are trying to do a balance on this space. So we want to write the rate of change of energy inside of the space here. So the way we'll do that is we'll say the amount of energy in the space. So D, we want the rate of change of energy in the space. And we estimate it as the number of moles of A in the space, as we did before, number of moles. And now we simply multiply by the enthalpy. So we've said the enthalpy is the energy per mass of our component. And then if we multiply by the mass of the component, then that's the energy content in the space. Of course, we define this on a mass basis, so we do need to multiply by a molar mass here. So that's one, but you can also define a molar enthalpy. So enthalpy doesn't have to be energy per mass, it can be energy per moles. So let's assume this is enthalpy per mole. So around this point on, assume H on a molar basis. Right, so we have a certain number of moles of A in the space, and we have the enthalpy. And then in that number of moles, we estimate the number of moles by taking the concentration and multiplying it by the volume. And we said that was 4 pi r squared delta r, right? So that's enthalpy. Sorry, that's enthalpy, and that's the number of moles. So this is molar enthalpy times number of moles. So that's the way we count the energy there. And then we want to, we want to associate this more with the temperature. So instead of enthalpy, we can rewrite this as the heat capacity CPA times a temperature, and it's T minus T ref. So T minus T ref. So we estimate the enthalpy by assuming, for example, that there is that we have a reference enthalpy. So we are doing all this on the basis of, so for example, if we are looking at this in the liquid stage, then we are saying, let's say we have a reference enthalpy, our reference temperature is here. And so, for example, if our temperature is here, then that difference, that tells us the energy content. So that's the energy content inside the space that we are looking at. Okay, any questions or comments there? Okay, so that's the energy in the space. And then the next thing to look at is the flux of energy across that space as well. So in fact, we need this picture again now. So, okay, let's do this as a new one now. Okay, now we need the temperature. We need the temperature difference. We know there's a temperature difference between these 2 points. So due to the temperature difference between these 2 points, for instance, we have a certain bulk conduction, right? And think about a bar of metal. If you apply heat to one point, then you'll get conduction. Heat will conduct along that bar of metal. It's the same in a liquid like this. If you have a high temperature at one point in the liquid, you will be conducting across that liquid. So in the case of conduction, we can say the conduction flux, and let's use Q for conduction flux. The conduction flux is, let's use capital Q, that is, conduction flux is equal to the conductivity. So, sorry, it should be a lowercase kappa. The conductivity multiplied with the temperature gradient, dr. And you can see the analogy with diffusion, right? In the case of diffusion, you'll have a diffusivity and a gradient in concentration. In the case of conduction, you have the conduction constant and you have a temperature gradient. And you are always diffusing against the temperature gradient. You are going from high to low. So that's your conduction flux. So we can say then that we are receiving energy by conduction from the inside of our space here. So when energy arrives fluxing in on the inside face here, then we have a contribution to conduction. So it's going to be plus, and then we have conduction itself is defined like that. And then we have to multiply by the inside surface area. So that's 4 pi r squared. And then we have, here we should just specify this is at position R. And then on the other side, we have a flux out of that space. So that's a loss from the space, so minus. And this is at position R plus delta R. And this is at R is R plus delta R. So that's our balance. And then if you follow all the usual steps, you can see that this is going to work out to be CA times CPA. The derivative of Tref. Tref is a constant, so that vanishes, leaving us just with T. And all this, I'm sorry, here, what happened? I forgot the equal sign here. And this was a plus and a minus, like, okay, let's just write, yeah. So all this equals, if you follow the usual approach, it's going to be kappa over R squared. And in here is going to be dr of R squared dt dr. Okay, so that's our energy balance. So if we solve this balance, then that's going to give us the gradient in temperature. Okay, now you may be relieved to know all of this, of course, we are introducing because of the section on analogies. So in all my sections, in all my tests, I'm not going to ask you about this. So Mr. Biela will be taking you through this material in more detail. So we are just covering this because of its consistency with what we are doing here, because everything is done by analogy now, right? So those the main thing I wanted to do with this, right? Maybe I went a little bit far with this balance, but the main concept I wanted to do to establish was the heat capacity and the conductivity, also enthalpy. So enthalpy is the way to relate mass to energy. Heat capacity is to relate enthalpy to temperature. And conductivity relates, well, it's the analog to diffusivity, right? So those three things are what we are looking to port over to analogies. So conductivity, so that's equivalent to diffusivity. And the other one was the enthalpy, relate mass and energy, and then heat capacity, right? What's the capacity to hold energy for 1 degree, for a 1 degree change, right? So relate enthalpy to temperature or energy changes to temperature changes. Okay, so with those three concepts, we can start to look into these analogies that we introduced. So we introduced the notion last time, right? So hopefully now that clarifies all these constants that we're looking at. So the mass transfer coefficient, we revised that concept. We showed through film theory that mass transfer coefficient relates to diffusivity. You can see heat capacity. So hopefully we are on the same page on heat capacity now as well. And there is this unexplained lowercase h. This is not enthalpy. This is a heat transfer coefficient. So this lowercase h is another analogy. It's analogous to Kc. So in the same way that Kc relates to diffusivity. So let's write that here. So we can say the mass transfer coefficient Kc relates to diffusivity. And of course, we have Kc equals dAe divided by delta, delta being the film thickness. And we can say here, in the same way that the heat transfer coefficient H relates to conductivity. So the heat transfer coefficient is related to the conductivity in a similar way. And we are going to call this delta sub Q, because the film thickness for heat transfer might not be the same as the film thickness for mass transfer. The analogies say that they are. It says that there's a relationship, that it's the same whirl, but we haven't said that so far. But so at this stage, the film thickness for heat transfer is in principle different to the film thickness for mass transfer. Okay, so hopefully that's a detailed look at how heat transfer relates to mass transfer. Okay, so that's what that H is. So when we look at these relationships, we can see that's what the H is. That's like a Kc. So this is like for heat transfer, the Kc that we see in mass transfer. And so all these relationships, right? The Reynolds analogy, the Chilton-Colburn analogy, these are trying to find relationships among the different balances. So in this one, we have an emphasis on mass transfer, and this one on energy transfer. But we can define equivalent dimensionless groups. And when we say that they are actually equal, then we start to find relationships among these different quantities. And so even though you have a problem that's affected by heat transfer and you only happen to have mass transfer measurements, you can still use what you learn in the mass transfer sense to assist your energy balance. So let's look at an example like that. So this first one doesn't actually use any analogies. This one just establishes a problem that we'll use more just now. So here we have a simple case. Sorry about that. So here we have a simple case of air flowing over frozen CO2. So let's just get it. So we have some slab here, and it's frozen CO2. So there's a slab of frozen CO2. And we are passing a stream which is flowing at a certain rate. So we don't, okay, here, diffusivity. Yeah, we actually don't have any information about how fast, they're 2 meters per second, right? So there's a flowing stream 2 meters per second that's passing over this frozen CO2. Two meters per second. And this is air, right? Is it air? air, right? So that's air. So air is flowing, and we have some other information. So the exposed area is 1 × 10⁻³ meters squared. So the area here, let's just write that, 0.001 meters squared. So we know the surface area. And so the carbon dioxide is going to sublime into that, right? So sublime sublimation, your molecules from the solid are going directly into the gas. So without first going into the liquid phase, we are subliming directly into the gas. So CO2 is leaving the solid and entering the gas, and that's on the molecular basis. So we have molecules leaving into the gas. And we are told that we actually know the rate at which this is happening, 2.2 × 10⁻⁴. So this sublimation rate, 2.2 × 10⁻⁴, is that 2.29? Yeah, 2.29 × 10⁻⁴. That's our sublimation rate. And we are given the air temperature and pressure. And we are also given the diffusivity at that temperature. So we can say dCO2 and air, the diffusivity of carbon dioxide into air is known. So that's 1. And then we also know the viscosity of the air. So the viscosity of the air, and that's given to us in pure SI units, 1.55 × 10⁻⁵. So rather meters squared. Right, so that's the viscosity of the air. And okay, so that's all the information that we have. And so first we are asked to figure out the mass transfer coefficient, right? So to work that out, the mass transfer coefficient, of course, we can say the molar flux is equal to the mass transfer coefficient multiplied by the concentration as a driving force, so CAS minus CA bulk. And we are given the actual rate in terms of moles per second. So this is the actual loss rate, the molar rate of loss. So if you read here, right, this is the molar loss rate of the block. And so maybe this block of CO2 was sitting on a mass balance or something like that, so that we can actually just observe the mass change with time and convert it to a molar change with time. So that's something that's measured. And what we've written here is actually the molar flux. So we need to use this. So let's relate that. So we can say NA dot is what we are actually given in the problem. So that's the molar loss rate. So we need to divide by the area, and the area is given to us. So now we have an area here. So that's the area that's given to us. And we are given the actual flux. Which one was it? I don't think we wrote it. So we are given not the flux, the molar loss rate, and we are given the area. So we can work out a flux from that. We are trying to get to Kc. So we just need these two things. Now let's think about the bulk concentration of, and the diffusing component is CO2, right? So if we are considering the loss from the solid into this gas, then we are going to assume that the CO2 concentration is approximately 0. Of course, it's not exactly 0. Today, it's in the media and everything that with global warming and rising CO2 levels and all of that. But in terms of comparing the amount of CO2 in the air with a solid block of CO2, or rather the saturated air near that block and the bulk here, this is a much lower concentration. So we could take this as approximately 0. And then we just need the concentration just at the surface. So to do that, we can think about the concentration at the surface. So we do need the concentration in the gas that's close to the surface here. And that concentration is not the same as the concentration in the solid, right? So in the solid, there's a certain concentration, but the mass transfer coefficient we are concerned with is in the gas here. So we need the gas phase surface concentration. So the gas phase total concentration is the pressure in the air. And of course, if your pressure is low enough, if your pressure is below 15 atmospheres, then PV equals nRT applies, right? Your ideal gas law. And then we can say concentration equals moles over volume. And so from N over V here, we can say that's equal to P over RT. And so the concentration on the surface CAS is equal to the mole fraction of A times the total concentration. And so if we have the, let's see, what do we have here? So the air is at that CO2, CAS. So this PA, so that's the pressure. So I believe what's done here is that we've simply looked up the CO2 saturation concentration. So we do know the partial pressure of CO2. So this is another thing that's tabulated in chemical engineering. The partial pressures of our species can be tabulated for a given temperature and a given pressure, right? If you look in your handbooks, you'll see, even in your course textbook, you'll see that we have the partial pressures defined, the saturation partial pressure for a given temperature and a given total pressure, we can get the partial pressure of a component. And so those are obtained quite simply with experiments where you might have, for example, a liquid and you seal in a gas here and you wait for the liquid and the vapor to equilibrate, and then you get the saturated amount of your component in the gas phase. And so there's a saturation partial pressure. And we can say that right next to the surface here, we reach the saturation partial pressure of CO2. So on the surface, we can reliably say that's the partial pressure there. So, so instead of working in terms of XA, we can say that's all just equal to the partial pressure of the CO2 divided by RT. So that's how we get CAS. So that's a piece of additional information we have to look up. We have to get that PA. And then with that, we've got CAS. And then everything is defined from there, because we said CAB is 0. In the bulk, there's approximately very low concentration of CO2. CAS we've just worked out. And the molar flux we can get by dividing the mass rate by the area. So everything is known except for Kc, and so we can calculate a Kc here. Okay, any questions or comments on that? And so this doesn't use any analogies. This is a straightforward application of molar flux. So this is something we are familiar with, right? Now, what we want to look at is, right, I'm skipping over this. This is a different problem altogether here. So in this, this is a continuation of the problem we've been talking about. So it's saying here, now what's the heat transfer coefficient? So it's saying, yes, in that first example, we worked out a mass transfer coefficient. Now, what's the heat transfer coefficient? And you see, it's not giving us any additional information. Right down here is the solution, really. Up here, there's no additional information given to us. And so if we are now suddenly asked about the heat transfer coefficient, we would say, well, then let's go back and look at the heat transfer information. And you look carefully in here and you find no information about heat transfer. There's nothing in here about, oh, the temperature changed by this and, you know, and so on. You do have temperatures, but that's not related to changes and heat transfers or anything like that. So there's no information here about heat transfer. And yet the question is asking, what's the heat transfer coefficient? And so I'm being a little bit dramatic here, but the reason that we can answer a question like this is because of the heat transfer, the heat and mass transfer analogies. So the analogy says that it's the same form, right? That the form where the mass transfer, right? So far we've talked about the mass transfer form. When we were working out a Kc, we saw earlier, Kc relates to the foam thickness and all that. So according to the Chiltern-Colburn analogy, the heat transfer form is the same as the mass transfer form. And so if we accept that, then we have this nice relationship available to us. So the Chiltern-Colburn J factors are defined like this. And we showed, I think it was 2 lectures ago, how those dimensionless groups arise and so on. So, so we have this relationship by saying the forms are the same. And if that's the case, then you can see the V infinity, the flow rate in the bulk. If those cancel, what else? We don't have to, I think nothing else cancels. And so we can solve for H. And if you look on this side, you've got the density. So the density, it will be the density of the air, the heat capacity, and the mass transfer coefficient. So this is what we just worked out in example 1. And then there's the Schmidt number and the Prandtl number. So the density and heat capacity, we can look those up for air. And then, right, so that's given here. And if you look in your textbook, you can just look that up in the table. And also the Prandtl number is defined for air as well. So the Prandtl number, you can go and calculate it. So if you go to our definitions for the dimensionless groups, the Prandtl number here. So you can take the diffusivity of air and the heat capacity and the viscosity. So you can look all those up and you can work out the Prandtl number. But in this problem, it's just given to us. So that's been done already. And then the Schmidt number, that's the viscosity. So this is the so-called kinematic viscosity. So the viscosity divided by the density. So that's given to us. And then the diffusivity. And this diffusivity was given in the original problem statement. I think we actually didn't use it there. But we need it here now. So the Schmidt number can be worked out as well. And then that's basically everything we need. So simply by looking up the published measurements or the published parameters for our species, we can take advantage of the Chiltern-Colburn analogy, and we can answer a question that relates to constants that are not found in our original problem. So hopefully from that, you appreciate the power of these analogies. Okay, any questions or comments on that? Okay, then there are more problems of that nature in the tutorial. So if you look in the Dropbox folder, there are more files for tutorials, so we can work through more of those on Friday. But that's the approach there. Then, of course, the thing you've been waiting for about the test, right? Okay, so I guess this is not relevant to the video. 1 second.